Terpenes and terpenoids are the largest group of known natural products, with more than 80,000 known molecules. Many of them have medical and industrial applications. One possible anti-inflammatory agent is cyclooctatin, whose precursor is synthesized by the enzyme CotB2. The substrate is GGPP, and in a series of carbocation reactions, it transforms into cyclooctate 9-ene-7-ol in 11 distinct chemical steps, which is converted to cyclooctatin via a series of additional enzyme reactions. In this video, we'll demonstrate how to set up a docking campaign of key intermediates in this reaction. As these are carbocations, we cannot use CGenFF to obtain force field parameters, so we generated these in advance, as published elsewhere. In addition, we would like to perform final scoring using a CHARMM method that better describes the carbocation's geometry and charge distribution. For this, we'll use the HF3C method implemented in CHARMM via the QChem software. We'll prepare the system for docking on CHARMM-GUI, then download and run locally. Note that you'll need a local copy of QChem and CHARMM compiled with QChem support. The protein structure we'll use is 6GGI. 6GGI is a crystal structure of the Streptomyces melanosporophaciens CotB2 enzyme, bound to a diphosphate and 3 magnesium ions and an intermediate analog denoted as EXW. To begin, go to EnzyDocker, type 6GGI, and click Next. We select all the segments we want to include: the first protein chain, the first 3 magnesium ions, the phosphate cofactor named PPV, and EXW, which is the substrate mimic. We also select the water molecules of the first protein unit and click Next. For most organic ligands and cofactors, we leave reading heterochain residues with default settings. In the case of metal ions, one should specify the oxidation state through rename to and CSML search. In this case, we do not need to modify anything, so click Next to generate a CHARMM-compatible PDB file. When it finishes, you should inspect the structure to ensure that it was read correctly. Just like in the previous video, we need to set the binding site location, grid size, and grid resolution. Here, 20 angstrom should be enough as it contains the entire ligand. To define the binding site, we will use the first method, which selects residues around the ligand EXW. Water molecules inside the grid are already marked as flexible, and in this case, we don't mark any other residue as flexible. Finally, we inspect the resulting grid and click Next. The experimental ligand is a mimic of a reaction intermediate. To add intermediates of the native substrate, we use the ligand upload options and upload mol2 and matching custom-made PRM and RTF files with matching names and click Next. On this page, we can edit the structure of the cofactors or the ligands through a 2D sketchpad. We mark the 3 magnesium ions as cofactors along with PPV and open PPV to ensure charges and protonation states were read correctly and fix them as needed. We choose the Matching Elements option to let the cofactor keep its experimental coordinates, then click Next. From the list of ligands, we eliminate het F and het G, keeping only the ligands we uploaded. Click Check to ensure that CGenFF can parameterize our ligands. Since we got a green check, we can continue. In case we want to use the experimental ligand as a reference structure to guide our docking, we can define the reference ligand at the bottom of the screen. In this example, we will do free docking, so simply select Na. Then we click Next. Here we can inspect the protein, cofactor, and reference ligand structure and set a few docking options. We don't need restraints in this case. The other settings govern the sampling conditions as described in the previous demo. In this case, we want to score our carbocation poses using quantum methods, so we tick the QMMM option. While waiting for docking to complete, we go to our user profile, choose Job IDs, select our EnzyDocker job, and go to the 4th step of EnzyDocker. Here, we want to retrieve the relevant files for running the job on a local machine with QChem. Click CHARMM-PDB and download the entire project. The directory 6GGI contains all files needed for an EnzyDoc run, and this is the one we transfer to our Linux server. On this machine, we have a version of CHARMM compiled with QChem support. To run EnzyDoc locally, we only need to adjust the paths under dir0 in stream/param.str. We can also update the path to a scratch directory on a scratch disk under scr1dir, and a path to the CGenFF executable under CGenFF, although we will not be using CGenFF in this video. We also have to update the path to a Python interpreter with EnzyDoc's package dependencies in scripts/python-wrapper.sh. EnzyDoc requires the Python packages NumPy, Pandas, OpenBabel, and RDKit. We should also add executable permissions to all shell and Python scripts under the scripts directory. If an empty file with the name of the project is found in the doc directory, we should remove it. Finally, we can run our job from the doc directory. We can follow the process using the enzydoc.log file or the full CHARMM output files. The result will be in the results directory, and we can visualize them using tools like Pymol and VMD. We can also run it with different docking settings under the stream/userparam.str file. Please check the EnzyDoc GitHub for more information.